Hello, so here in this we're going to be looking at section 2.4, which is going to be solving equations with variables on both sides. So far all we've seen is equations with variables on the same side where we were able to combine them like terms. We're going to see a different scenario today. So to solve equations with variables on both sides, you must move like terms. Our goal is that we're going to want to have our isolated variable on one side and our constant on the other. Alright, and you can see the example right there of the 2x is equal to 8. So just as always, we're going to want our x on one side and our numbers, known as constants, on the other. So let's take a look and also compare and contrast these to the problems that have variables on both sides with what we've previously learned of variables on one side. We're going to solve the variable and check our answers, at least mentally, here for us. Alright, now, one thing I want us to notice is that our variables are on different sides. If I draw a line down through this equal sign, we can see the two different sides of the equation. So with this being said, I can't combine them like we were doing the other day, because one question is, where would they go? Right? They are unable to join up because they are separated on different sides. Here is what we're going to need to do. You're going to pick one of them, doesn't matter which one, either the 7k or the 5k, and we're going to move it. And when we want to move things, I have to move it with addition and subtraction. That way, we're keeping our equations balanced. I like to avoid negative numbers, so instead of subtracting 7k from both sides, I'm going to subtract 5k from both sides. And here's what will happen when I do that. Alright, on this side of the equation, it's going to cross off. Now leaving us with over here a 2k, subtract 4, is equal to our 16. So once we do that, we are now back to a regular two-step equation to where I could add 4 to both sides. Alright, get that to cancel out. And then we have our 2k is equal to 20. Divide both sides by the 2, and we will get that our k is equal to 10. Alright, now since this was the first one that we did with variables on both sides, I am going to go back and have us check it. We check it in the same way as we would check any equation. You go back to the original equation, except you leave yourself some space to plug in the number that we solve for x. So it's going to look like this, 7k minus 4. We're hoping that it's equal to 5k plus 16. Alright, so on this here, let's plug in our 10. And check what we get. So here I'll get a 70 minus the 4 is equal to a 50 plus a 16. And we will see that on this side we get a 66. On this side we will get a 66. So there's our proof. This does indeed still work. Now we would have gotten the same answer if we would have taken a different initial step and subtracted 7k from both sides. As long as you're keeping things balanced, you can't mess it up. Right, and you'll see over here I drew the line through the equal sign to help us visualize the two different sides. As long as we are being fair to both sides, we're good to go. Let's look at another example. So on this one here, another scenario, I will engage with a negative this time, just to kind of show you that that's okay and that it is possible to still solve while doing that. I have variables on different sides. This time I'm going to subtract the larger one. I'm going to subtract a 9x from both sides. Right? When I do this, I'll cross off on this side. On this side, giving me a negative 4x plus 3 is equal here now to a negative 21. Now, once again, once we get it here, really quick two-step equation. Subtract 3 from both sides. We will get a negative 4x is equal to a negative 24. If I would have, back at the beginning, if I would have subtracted a 5x from both sides, your final step would have been a positive 4x is equal to a positive 24. I chose to subtract the 9x. My example ends up at a negative 4x equal to a negative 24, which those two negatives will cancel out. When I divide both sides by the negative 4, both ways would give me x is equal to 6. Alright, that's the general idea here. So I'm going to skip some of these. That way we can get us onto our practice quicker. But that's the general concept. Right, so let's take a look at, even when there's other things in our way. Right, let's take a look at an equation like this. Alright, now before I'm able to move around my variables that are on the different sides of the equation, we'll need to do some simplifying by distributing. So here we'll get a 6y plus 2 is equal to, and then when I distribute on this side, we get an 8y minus, because there's a negative 5, 20. So now I've got a general equation of variables on both sides. I like to pick the smaller variable to move. That way I am not making myself have to deal with unnecessary negatives. So I would subtract a 6y from both sides. Once we do that, we've got 2 equal to 2y minus 20. You could proceed on solving this two-step equation, adding 20 onto both sides, getting 22 is equal to 2y, dividing both sides by the 2 to get that our y is equal to an 11. Right, and then it's always nice to, on more complicated problems, to double check that by plugging it back in. And if you plug that 11 back in on your own time, you will indeed see that it checks out. It will make both sides of the equation equal. Let's come right over here on to this problem. This problem is going to be very important to understand. I'm going to have to distribute here first to get a 2n plus 2. Then when I distribute here, I'm going to get another plus 3n minus 3. And all of this is equal here to our 4n. Now, I want us to notice something. On the right-hand side of our equation, I have variables 2n and 3n. They are on the same side. So our rule of what we used to do with this still applies. Before I interact with the other side of my equation, I need to combine these like terms. Since they are on the same side of the equation, I will not do anything like this. I won't subtract 2n and subtract 2n. That would be wrong because that's not keeping my equation balanced, because I did something on the right-hand side but not the left. Instead, they will combine just like they would have before I showed us this lesson. Right? They would become a 5. Sorry, let me switch back to the marker. They'd become a 5n. And then I could also combine these like terms as well, of 2 minus 3 to get a negative 1. And all of this here is equal still to our 4n. Now we have variables on different sides. Now I've already got my constants on the right-hand side, so I'm essentially saving time by not moving the 4 in to the right, because then I'd have to move the -1 to the left. And here's what we'll get. We'll get a -n is equal to a -1. Remember, we do have to fully isolate n, so I'd want to divide both sides by -1 or multiply both sides by -1 to get that n is equal to a +1. Once again, if you plug n is equal to 1 back into your original equation on both sides, everywhere you see an n, you plug in a 1, you will get an equation that holds true, that will stay balanced. So you can check these just like you can check any other type of equation that we work with. Now that we're working with variables on both sides, this is going to open up a new concept here, a new can of worms, if you will, of something that can happen. And so let me explain that to us. There's something called an identity. Right, and if you think of the word identity of yourself, like what's your identity? It's yourself, right? And that's what it really means here in this concept too. An identity is an equation that's true for every value of x. An identity is when you have something equal to its exact same something. It's like that equation's looking into a mirror, right? If you're looking at a mirror and you move your arm, the mirror does the exact same thing. And if you take a look at this, no matter what I plug in for x, positive number, negative number, fraction, it will always ring true because something plus 1 is always equal to the same thing plus 1. That's an identity, right? And so with that, that means it has infinite solutions. We'll also see this visually on a graph later in the year, but it has infinite solutions. So up to this point now, we've seen equations that have one solution, a specific number. We'll see equations that have infinite solutions, to where no matter what I plug in for x. And then there's also an equation that will never be true. An equation that is never true will have no solutions. And that's what we'll write. Sometimes we will write no solution as our answer. Here's an example. 2x is equal to 2x plus 1. The reason this will never have a solution is because this 2x is equal to this 2x. But this 2x also has a plus 1 with it. So there's no way to balance it out. This would be like having someone that's 1 year older than you, right? No matter what you do, as you're growing older and older, they are your age plus 1. You will never catch up to them. There's no solution. You'll never be able to find a number for x here that would work. Right? Now, the only thing you have to look out for is that sometimes these concepts are in disguise and you might not recognize it right away. If I showed you this equation, they don't look identical yet. However, you'll often find if you simplify things through our different properties, so in this case I'm going to distribute, I'll get a 10x plus a 12. You'll then see, hey, that's the exact same thing that's on the other side of my equation. And anytime we get the exact same thing on either side, that's when I know it's no solutions. Say you didn't recognize it still, and you tried to keep solving by subtracting 10x from both sides, right? I want to combine my variables. If I subtract 10x from both sides, notice what happens. This cancels out. This cancels out. I get another statement to where it's an identity, right? Once something is an identity, no matter what you do to both sides, it will always remain equal. This would be infinite solutions. And you do want to write it out because that's the answer. Infinite solutions. Okay? So, in a similar concept, you will also see equations that have no solutions be disguised as well. That's what's going on here, because I have some like terms. I've got a negative 3m, positive 12m. I could combine that to get myself a 9m plus 5, and it will be equal to, on the other side, a 9m minus 4. These are a little harder to spot, but what will denote when you have no solution is that you have the exact same variable term on each side, but then it's paired with a different constant. I have 9m and 9m, however, one of them is paired with a negative 4, the other one's paired with a positive 5. If I tried to keep solving by subtracting 9m from both sides, here's what would happen. I would get a statement that doesn't make any sense. Negative 4 is equal to 5. If all your variables cancel out and you're left with a scenario that doesn't make any sense, that is a scenario where you have no solution. Alright, so this problem here, it says geometry. This is something that you will see in geometry. It's just a fancy way of having us continue on with our learning of variables on different sides. This is a concept in geometry called vertical angles. When you have two angles opposite of each other, they are set equal. We're not really going to be held accountable to viewing that, but it's just to show us some applications of what this might look like, and you'll definitely see it in a geometry class. But when you see a problem like this, all it's telling us is this. We have 6x plus 3 is equal to the other angle, which is 8x minus 21. So we could take this setup here, and we'd be able to solve this out for our x. Alright, how could we do that? Alright, one more time on this, and I'll try to move on to get you guys onto the practice after the back side. So we'll subtract 6x from both sides, right? I had variables on different sides. I had to move them with addition or subtraction. And if I'm moving my variables over to the right, that means I need to get this 21, my constant, over onto the left, right? So if I kind of do both steps at once there, now I'll have a 24 on the left is equal to a 2x, divide both sides by the 2, and we will get here that our x is equal to 12. All right, and like I said, that's something that we'll see in geometry. You might see some of those on the homework. I know the first problem on the back side here is just like that. It's labeled as a U try, but we will we'll leave it for now so that we can take a look at this word problem and then get you guys onto the practice and then onto the homework as well. Alright, so we have currently it takes me 1.5 hours to download my new computer games. If I update my computer, it will decrease that time to 1.25 hours per game, but my update takes 8 hours. Will it be worth it for me to upgrade? How many games will it take for me to download to make the upgrade worthwhile? This will be a very good question when we work in Chapter 3 with inequalities, but this is what variables on both sides helps us do. It helps us weigh two different situations to find what's going to be a better deal for us. Here's how this setup would work. All right, we're going to make x our hours. All right, so in one situation, it takes 1.5 hours. Wait, no, sorry. X will be the number of games that's what we're looking for. It takes 1.5 hours to download a game. If I set this equal to the other scenario, which is an 1.25 hours per every game plus the 8 hours. Solving this situation will help us find out which one of these scenarios will be better. It'll make more sense in Chapter 3 when we're using inequalities. But it's nice to preview here. Now, obviously, if I'm downloading one game, this side here on the left would be a better option because it just takes an hour and a half. Okay? However, if I put one game in on this side, I'd have to update for 8 hours only to save 0.25 hours. But if you think about it, at some point, the right-hand side will be a better deal. If I was going to be doing 1,000 games that are going to download, obviously I'm going to want that faster download speed because the 8 hours it took for me to upgrade my computer would be canceled out by the faster download time. So solving this equation will help us find where is that break-even point and then what should I do depending on how many games I'm trying to download. Let's solve this equation. I would want to subtract 1.25x from both sides. If I did that, we'd have 0.25x on the left-hand side is equal to 8. Now if I divide, because this is 0.25 multiplied by x, if I divide both sides by 0.25, I would get that x is equal to 32 games. All right, so that's the break-even point, because remember, we're working with an equation where things are equal. But what this would tell me, it'll make more sense in Chapter 3, is if I was going to be downloading less than 32 games, I would want to keep my computer in its current state. However, if I'm going to be downloading more than 32 games, that's when it's going to be worthwhile for me to do the 8-hour update to get a faster computer. All right, and that's what the power of variables on both sides is. It'll let us answer lots of questions like this, which is really what we want math for, finding better deals, saving time, all the different applications of that. So what you'll be able to do now is I have some practice here available of various types. You got some distributing, some decimals on there. So I do want us to sort through these 3 practice problems to see if you can't identify any questions while we're still on this page, looking at your notes. Then what you can do is begin on the section homework for this section posted on the agenda on Plus Portals and start to give that a look and spend time on that.